have the official Aaron walking through in front of the camera. Come on, Aaron.
I'll even follow.
It'll be, you know,
Just trying to.
for posterity. It'll be in cyberspace forever. All right. So let's see. There's another problem set being prepared. It will be coming on the web tomorrow. Another 2-week assignment. Just to give you a little bit of a preview of what's coming, we'll have about 3 more problem sets through October, November, and then there won't be any more homework, and there'll be the final project, which we'll discuss a little bit more as that time approaches. But basically, the idea is to, everyone will be have the opportunity to explore a topic of interest to them and do some research, read some papers, and write a review article about some topic in atomic physics. Okay, so it'll be a final paper. All right. So let's see. Last time, so we completed what we're going to do this semester in terms of the discussion of atomic structure. We have sort of the basics, I think, under our belt. We have some ideas of what all of these, all the different quantum numbers are and how we describe the structure of multi-electron atoms. And what we're going to be doing for the remainder of the semester is thinking about the manipulation of atoms through their interaction with electromagnetic fields. Okay? So to do that, we started at the end of the last lecture. What we did is that we wrote down the sort of fundamental minimal coupling Hamiltonian, so to speak, which has the, in terms of the vector potential and the scalar potential. And then under a particular gauge transformation, we can rewrite that in a way that is convenient in the context of the interaction of atoms with light, or generally in the non-relativistic approximation, as we'll explain in a moment. And so when we did a particular gauge transformation, we can rewrite the Hamiltonian kind of separately as the atomic Hamiltonian and then the interaction of the atom with the electromagnetic fields. And that takes the form, that particular transformation is known as the Auer-Zeno-Woolley transformation. And when we do that, we have the following form for the, this is really an exact form. We haven't really made any approximations yet. So we have, if there is a sort of a scalar field coming from the near field, say I have some capacitor plates and I have some quasi-static fields in the presence of charges, so the electrostatic part of the interaction is here. And then we have the interaction of the electric field associated with an electromagnetic wave, would be represented here, interacting with the polarization density, that is to say, this is the dipole density associated with the collection of charges. And then we have the magnetic interactions in terms of the magnetization density. The magnetization density here is due to the electrons, which have both orbital and spin components. And if we wanted to, we could include a small nuclear contribution of the nucleus interacting with the magnetic field as well. Okay? So this is our fundamental Hamiltonian that we begin with. we then are considering the situation where the fields have characteristic wavelengths lambda, right? And what our atoms are of size on the order of the Bohr radius. And we're going to consider the case where the wavelengths are much, much bigger than the size of the atom. For example, optical fields, or infrared fields, or even UV. Generally, this is a good approximation. Right? Another way of saying this is if I look at the wavelength in terms of the frequency of the transformation. I mean, the frequency of the field that's oscillating. I could say this in another way. So if t is the period of the oscillation of the field, what this is saying is that the sort of speed of the atom for charges that are moving across that distance in that time is very slow compared to the speed of light. So really what this is equivalent to saying that for charges that are moving in that period over that distance, if that speed is non-relativistic, well then we have what you remember, I hope, from most classical electromagnetism, the multiple extension, the multiple approximation. That is, the multiple approximation, you remember, in the context of electromagnetic radiation, says that if I have a collection of charges, localized in region of size A, then if the speed is non-relativistic, then the radiation of the moving charges or the accelerating charges is expandable in multiples. So that we think about our distribution of charges, and that distribution of charges has a monopole moment, an electric dipole moment, a magnetic dipole moment, an electric quadrupole moment, etc. And each of those moments generates a characteristic radiation. And the amount of radiation that's generated by each of those moments is not the same. That is to say, the terms that are low order multiple moments generate much more power in the radiation than the higher order multipole moments. The same thing is true for the absorption. If I think about an antenna, and I think about the antenna absorbing electromagnetic radiation, then it is the dipole, typically it's the electric dipole of those oscillating charges in the antenna that dominantly absorb the radiation. One talks about dipole antennas. It's no different in the context of quantum mechanics. In this interaction, again, as long as the speed of the electron is slow enough, or equivalently said, if the wavelength of the radiation is big compared to the size of the distribution of charges, then the dominant interaction terms, in terms of absorption and emission, are the terms that are the lowest order multipole moments of the charge distribution. So, with that said, we would typically, in order to look at the way in which atoms absorb and emit electromagnetic waves, or absorb and emit photons, if we want to think about that as quantum fields, we would take this expression and we would expand it in a multipole expansion. So, in a multipole expansion, our interaction Hamiltonian takes the following form. So, what is this expression? So what I have here, Q is the sum of all the charges. That is the monopole. D here is the sum of all the charges weighted by their position. That's the electric dipole. Mu here is the sum of all the magnetic moments of all the electrons. Let me ignore the nuclear spin contribution. It's there, but it's tiny. And then Q here, Q alpha beta, is the sum over all the charges times things having to do with the different components etc. And this is the electric quadrupole moment, etc. So here alpha and beta represent the x, y, and z. Alpha and beta run from 1 to 3, representing the x, y, and z coordinates of the positions of the charges. All right. So, and R here is the origin, which is taken to be the position of the nucleus, or the center of mass of the atom, of my origin. So under the assumption that the distribution of charges is small compared to lambda, I can expand about that center of mass, and then I end up with the familiar dipole expansion or multipole expansion for the interaction of fields and charges. And this becomes our quantum mechanical operator, where this is now an operator representing the dipole operator, the magnetic dipole operator, and the quadrupole operator. And each of these terms then has different effects on the interaction of the atoms with the fields. Now, this term here, if I'm talking about a neutral atom, is 0. It's there because maybe I have a charged atom, I have an ion, and this would be the term that would be important if I wanted to think about trapping the ion with, electrostatic fields near charged plates. But it doesn't affect in any way the internal degrees of freedom of the atom. That's to say, it doesn't affect the relative motion of the electron relative to the nucleus, and thus is not a term that has anything to do with the energy levels of the atom. The lowest order term that has to do with the energy levels of the atom is the electric dipole term. And then we have the magnetic dipole term, electric quadrupole term, etc. So this interaction, as we see it, of course, can have two kinds of effects in thinking about the effect on the atoms. One effect would be to shift those energy levels, and the kind of discussions we've already had. We looked at early on the Stark shift when we applied a static electric field to the problem, and we looked at the shift of the energy levels. We've also looked at the Zeeman effect, which had to do with the shift of the energy levels in the presence of a static or quasi-static magnetic field. But in addition, if I think about my fields as being time dependent and oscillating at a frequency that's near to one of the resonances as determined by the Bohr frequency, the energy difference between those levels, then we know that we will induce resonantly absorption and emission. And that's really where we're headed with our discussion in the next few weeks, to review the problem of absorption and emission through the excitation when we have oscillating fields oscillating near resonance. All right? So that's our setting here. And what we, of course, see from this Hamiltonian is that, well, we have, in looking at the observables that are the observables of the atom that couple to the field, they are generally tensors. The multipole moments of the charge distribution are tensors. We have rank 1 tensors, the vectors, and we have, in this case, a rank 2 tensor, the quadrupole tensor. And they're not only tensor, they're tensor operators. So what we need to do in order to treat this and understand how our atoms are going to absorb and emit radiation is review, or study for the first time if you've never seen it, the theory of tensor operators. So let's begin that discussion today. So let's just begin by recalling, let's think about tensors. Let's think about, just remind ourselves from classical physics what we mean by a tensor. And tensors are all about the objects that behave a certain way under rotation in 3D. So, well, to think about a rotation, of course, rotations are defined, and how a rotation is defined is thinking about how position changes under a rotation. So if I have a position vector, and I rotate it to a different position about some axis, then we have a rotation transformation. And that rotation transformation is defined by the action of a matrix on the coordinates. So if I were to write x sub I as the coordinates, then the new coordinates of the new vector are related to the old coordinates through a rotation matrix. Okay? So rotation matrix is a SO3 matrix. So I've written here coordinates with respect to the Cartesian basis. All right. Any object, a set of 3 objects, so I here goes from 1 to 3, a set of 3 objects that transform this way under a rotation is what, of course, we call a vector. Transforms like position under a rotation. In quantum mechanics, we can talk about vector operators. So a vector operator e.g. position operator in 3D is an object which under a rotation, whatever so if I have a vector operator here, generally V, under a rotation, transforms into a new vector operator in the same way that, say, position, this could be the position operator. Its components must transform according to the same rotation features. just like the classical vector did. So the components, the three components of the vector operator, for example, x, y, and z operators for position or momentum, px, py, pz, would transform according to this kind of transformation. How do we achieve such a transformation? Well, in quantum mechanics, we achieve such a transformation through a unitary operator. So, and it's typically denoted D, okay, associated with a particular rotation. Moreover, we know that since these rotations are continuous, represent the elements of a continuous group, they are generated by Hermitian operators. And we know that the generator of rotations is angular momentum. So for example, the generator of position rotation is the angular momentum operator R cross P. And so a rotation about a particular angle and a particular axis is generated by the angular momentum operator. What does it mean to say that this unitary operator generates rotations? Well, there's a few things I could say about it. One thing I can say about it is that if I have this picture over here with R and R prime, and now I think about this not as a position, but a position eigenvector, like that, then the action of this operator on the original position eigenstate is the rotated position eigenstate. Said another way, we can think about this as the action on the position operator.
There's no way of turning that back into the exit.
As a unitary transformation. So this is all operators now, which is to say that the coordinates or the transformed position operator has components x sub I prime. They are transformed according to the SO3 rotation matrix. And thus, we define, according to this, a vector operator as an operator which, under the action of a rotation transformation, this is the I prime, so a collection of three operators which under a rotation transformation as accomplished by a unitary transformation generated by angular momentum. If it transforms this way, we say those are three components of a vector operator. Examples: position operator, momentum operator, are rotations, are vectors, which are vectors under rotations generated by the orbital angular momentum. Now, we can re-express this in a slightly different way by looking at, if I look at this for when theta becomes a very small infinitesimal rotation, then our unitary transformation is infinitesimally close to the identity. And this transformation then can be re-expressed in terms of a condition on the commutation relation. For example, position transforms according to this relation because it satisfies the commutation relations. That is equivalent, if I plug this in to this expression and re-express the Rij's appropriately, then the fact that position behaves this way under rotation is equivalent to saying how it commutes with the generators of rotation, in this case, orbital angular momentum. Okay, I'm using now the Einstein summation convention. Everyone's familiar with that? More generally, we say V is a vector operator under rotations generated by a general angular momentum operator, which may include spin angular momentum. It need not only be orbital angular momentum. We say that it is a vector under rotations generated by J if, and this would be the same expression here, express D in terms now it would have, instead of L, it would have J, if well, I guess because I'm keeping H bars around, I'm going to put an H bar there. And then soon I'm going to set H bar equal to 1. J sub I, I'm sorry, V sub I. Just got myself confused about the sign. Let me double check something. Yeah, it's got to be down this name. So that's another way of saying that V is a vector under rotations generated by J. Either I can look at it in this form, where D has this form, now generated by rotation generated by J, or equivalently, I can express it locally in terms of the commutation relations. Okay?
So it's, if it commutes, then you know if you write D that way, you'll get the rotation matrix.
You mean if the commutator is
Yeah.
this? Yes. Right.
And vice versa.
And vice versa. Because the infinitesimal generation of a rotation ultimately determines the whole group. It's the Lie algebra. So those are vectors and vector operators. But as we said, what we are more generally want to talk about are what are called tensors. Oh, by the way, in case you have never seen this, there's a little bit of confusion here, which is I said these rotation matrices are in the group SO3. But these unitary operators are generally, because they must include spin, in the group SU2. SU2 is not the same as the group SO3, but there's a complicated geometric relationship between them. They're quite similar. One is what's called the universal covering group of the other. We can talk about Lie algebras and manifolds and have a good old time for weeks on end talking about the differential geometry of these groups. But the point is that the generator of rotations in quantum mechanics, not the generator, but the group of rotations is the group SU2, and nonetheless, its operation on the components are expressible this way, where these are SO3 matrices. Subtle little point there. All right, so what is a tensor? So a tensor, we talk about a rank K tensor as an object with K indices. So I have, let's just think about this classically. I would think about index 1, index 2, index k. In the same way that I express this this is in some sense with respect to a basis, I can express this in a basis independent way by summing all of these indices from 1 to 3, and then look at outer products with all the basis vectors. Okay. So in the same way that the vector was a geometric object, but I can think about its components in a basis, I can re-express that in terms of multiplying the components by basis vectors. And these outer products are the basis vectors of the rank K tensor. Okay? And there are 3 to the K such objects. All right. So, because we know how each of the basis vectors rotates, transforms under rotation, then this object is a tensor if its components transform a particular way under those rotations. So a generalization now of this expression here, well, this is the quantum mechanical version, but let's talk about the classical version, is that this guy is a tensor if its components transform according to the following rule. So I have a set of k rotation matrices, and I operate each rotation matrix on each index. So, in the context of a vector is a rank 1 tensor. That's just the case where k is 1, and that's the rule we already established for the definition of the vector. Of course, a scalar is a rank 0 tensor. Okay. And then we have rank 2 tensors, etc., etc., etc. Now, from this definition, we see that if I take the note, if I have two vectors, if V, well, let's just say, I don't want to have too many letters. If A and B are vectors, then the outer product of two vectors is a tensor. I mean, that follows trivially because each one of these things rotates according to one of these matrices. So I have two of them, and so for rank 2 there will be two matrices. That is to say, if I define Tij as Aibj, then this is a rank 2 tensor, because Aij's rotate and Bij's rotate. Now, in the context of a rank 2 tensor made of the outer product of two vectors, it turns out we can look at this and break it up in a way that is gives us some geometric understanding. In particular, Tij can be re-expressed in terms of the sum of three pieces. This Tij, the one that, before I did, I guess I should, I haven't talked about the tensor operators, but I'll get to that in a moment. Let's talk about the classical tensors. So I'm going to break this up into three pieces that I will define with this superscript, where the following is true. This is equal to 1/3 delta ij times the trace of t, which in this case is a1 b1 plus a2 b2 plus a3 b3. The trace, you remember, is the sum of the diagonal elements. And so the diagonal elements is when I equals j. This, of course, is the same thing as 1/3 delta ij b. I am defining Tij superscript 1 as the antisymmetric part of the tensor, which in this case is Aibj minus A J B I, which is the same thing in this case as 1/2 epsilon I J K, the cross product. And the IJ2 is the traceless symmetric part of tensor. So I've broken this up in a way that isn't particularly motivated at the moment, but it's true, right? If I add this plus this plus this, I get Tij, right? Because the trace cancels here, and then I add these two together and I get Tij.
That's probably Ji, right? In the
It
symmetric.
is indeed, sorry. Okay, so this is a, this tensor is antisymmetric. This is symmetric and traceless. And this is the identity. Right, this delta Ij is the identity matrix times a constant. So I've broken this up into these three pieces. What, oh, by the way, you know what I mean by antisymmetric? It means that if I reverse, the antisymmetric means that if I reverse its indices, I get minus the matrix back. Tji is minus Tij, and Tj. Okay. So, why did I break it up this way? I broke it up this way because these different objects behave differently under a rotation. So we know there are 9 components of the original tensor, right? It's a 3x3 matrix. There's 9 components. And generally, we would imagine all those 9 components to transform into one another under a rotation. But that's not exactly true. Under a rotation, Tij goes to itself because the identity matrix doesn't change under a rotation. Under a rotation, an antisymmetric matrix goes to another antisymmetric matrix because a rotation just rotates this cross product to the rotated cross product, A prime cross B prime. And moreover, then, what's left after rotation is Tij2 goes to itself. So the point is that under a rotation, each piece of this tensor rotates into itself. And thus, what we say is that this tensor is reducible into irreducible pieces that rotate independently under rotation. They don't none of this tensor gets mixed with this tensor. These are sort of more geometric units. So these pieces are the TIJs. These are what are called irreducible tensors. In fact, they are irreducible tensors in Cartesian coordinates. Let me come back to this a moment. Let's think about what we now mean in quantum mechanics by a tensor operator. I didn't fix that, but so we define the rank K tensor operator as a collection of operators with these same indices, such that under a rotation as generated by the rotation operator, it transforms, its components transform such. So this is a tensor operator under rotations generated by the angular momentum operator J. Now, the fact that these tensors generally decompose into different objects that behave differently under rotations makes this not the most convenient way to express tensors. What we notice here, if we look back at our irreducible tensors, and for this particular case, we notice something, maybe a particular pattern here. If I look at this object, I see that in order to specify this object, I only have to specify one component, one number specifies the entire tensor. It's just A dot B. This number tells me what this tensor is. In order to specify this, I have to specify three numbers. They are the three components of the cross product. How many numbers do I have to specify this matrix or this tensor? Well, it's symmetric, which means I only, for one thing, I only have to, whatever is on one part of the diagonal is equal to the other, so I only have to specify the three numbers off diagonal. Then there are three numbers on the diagonal. However, the trace is 0. Thus, the sum is constrained to be 0, which means one of those numbers is dependent on the other two. So that's a total of 5 numbers that specify a symmetric traceless tensor. Okay? And of course, that adds up to 9, as we expect. Now, a little bit of numerology here. If I define the number of components, if I define the irreducible tensors T sub k, Tij, the number of components in that, independent components, is what? In this particular pattern, what we see is 2k plus 1. Now that's not a proof of anything, but we kind of remember 2l plus 1 or 2k plus 1 is the number of components, independent components, of an object with magnitude of angular momentum j. Right? If I have j, there are 2j plus 1 different possible projections or eigenstates. So one way, and we'll now revisit this in the context of the tensor operators in quantum mechanics, one way to think about these objects is that there is an intimate relationship between irreducible tensor operators of rank k and objects with angular momentum magnitude k. So we see there is an intimate relationship, or at least we get some hint at the intimate relationship between angular momentum, objects that have angular momentum, and objects that transform a particular way under a rotation. Yes, sir.
On the notation, when you sandwich the tensor between d level and
Yes.
Can you this does apply to any rank tensor? Can you, for instance, can you sandwich a vector?
Sure. So, I mean, you know, if I look at, for example, the momentum operator, then, you know, this is e to the plus I theta. Let's do a particular example. Let's say I rotate this around the z-axis. Okay, I'm going to set h bar equal to 1 from now on. You can show, after a little bit of algebra, that this is equal to cosine theta px plus sine theta py. That's an example of this transformation for a rank 1 tensor, where I've applied a unitary transformation to this operator and ended up with this linear combination of these operators. That's an example of a rotation. I can think about more general tensors. So if I said, you know, I looked at, I have two particles, or I have one particle, and for example, I look at the quadruple tensor operator. So that's some charge density, and then I have Ri, Rj, minus a third, R squared. This is the quadruple tensor. Now I can call this an operator. If I put this operator through here, then I would rotate each one of these guys. And it would look like this. I mean, I'm not going to write it out, this is a giant mess. But the new components would be related to the old components through this transformation.
Operators themselves, the p and x's themselves are just rank 2 tensors, aren't they? P.
No, rank 1. Momentum is a rank 1 tensor, it's a vector. Angular momentum is a little bit more complicated because angular momentum is related to x cross p, so it's really, well, it's a pseudo-vector, or equivalently, it's the rank 1 irreducible part of a rank 2 tensor, xi pj, or the nth metric part of that is angular momentum.
That is a rank one.
Angular momentum, it's a little bit, it's a pseudo-vector, so it's a little bit, it's a really, there's some subtleties there. It does behave like a rank 1 tensor under rotations, but it's more like this. Okay. But here, what we want to do now is think about, this is, as written here, is incredibly messy, and it's missing this important geometry that there are irreducible tensors that are more geometric objects that don't mix together under rotation. So what do we take away from that? Well, what we say then is, let's, in some sense, the reason for this is that we use the wrong basis. So tensors are often more naturally defined in what's called the spherical basis. What do I mean by the spherical basis? This is not spherical coordinates, although there is some relationship to spherical coordinates that we will see in a moment. Let's look at consider a rotation about the z-axis by angle phi. So let's write down the rotation matrix, the SO3 matrix that corresponds to that rotation. Well, that's the familiar form of a rotation matrix where this is x, y, and z, right? Takes x and y into rotations, cosine and sine, and leaves z alone. All right? So, I ask you, what are the eigenvalues and eigenvectors of this matrix? Because they, in some sense, are the natural objects, the natural basis to consider if I'm going to be thinking about rotations. X and Y, in some sense, aren't natural basis vectors because they transform into each other under rotations. But the eigenvectors are left alone under rotation. So what are the eigenvectors? Well, we see one of them, the z-axis, is an eigenvector.
E to the I phi or minus I phi?
Well, those are the eigenvalues. So the eigenvalues, if you diagonalize this, are of the form e to the minus I q times phi, where q is equal to minus 1, 0, or plus 1. And what are the eigenvectors? Well, we'll call them e sub q, where q can be 0, plus 1, or minus 1. E0, well, that's the guy that, when q is 0, that's the eigenvector that does not, the rotation does nothing to that. So that's just the z-axis. That's clearly an eigenvector rotation. But x and y rotate into one another. So no matter what I do, it seems like if I choose diagonal, diagonal is going to change. How the heck am I going to get an eigenvector? Well, I can't in real space. There is no vector in the xy plane that transforms into itself under rotation. It rotates. So I have to move into the complex plane, and the eigenvectors are ex plus or minus I ey. And if I normalize it, 1 over 2. Now, of course, the overall factor in front of the eigenvector doesn't affect whether it's an eigenvector or not. And there's a convention that is annoying as all gets out, but it's there because of the relationship to sort of a harmonic set we'll see in a moment, that we define E plus or minus 1 as minus plus with that sign out front. It's important to keep track of that sign. So this vector, of course, x changes into y and y changes into x, but under rotation, this vector comes back to itself with an overall phase e to the plus or minus I phi. This basis is very important if you want to deal with angular momentum in quantum mechanics and you want to deal with tensors. You've got to get used to dealing with the spherical basis. Now, what else can we see here? Well, so I claim this is an interesting basis to consider when thinking about the tensors rather than the Cartesian basis. This basis is what we call the spherical basis. Oh, by the way, I should mention a few facts here, a few other facts. Notice, because we're dealing with now a vector space with complex numbers, we have to think about the inner product with the complex conjugation. So these vectors are orthogonal, but with respect to a dot product that looks like psi star psi. Did I shut it off? No. All right. So if I have a vector v, then if I define v sub q as the dot product with e sub q, then the vector must be written with eq star. Right, because of this relationship. Another thing we notice is that eq star is equal to minus 1 to the q e minus q. And this is another way you will often see this written with this lovely factor, minus 1 to the q up front, and then a minus e minus q. All right, so why did I bother with this? Well, let's do a little aside over here. Let's consider the components of position. So let's write R as EQ star X of Q. Okay, so X of Q here is the component of position with respect to this spherical basis. So X0 is just the Z component, and X plus or minus 1 is equal to minus plus X plus or minus IY over root 2. Now let's re-express this in spherical coordinates. This is R cosine theta. And this is equal to plus or minus R over root 2 sine theta cos phi plus or minus I sine phi, or minus or plus R over root 2 sine phi e to the plus or minus I phi. Do you recognize these? Maybe, maybe not. But recall y10 is equal to 1 over 3 cosine phi, the spherical harmonic. So what we see here is that the angular dependence of the components of position with respect to the spherical basis are the angular dependence of the spherical harmonics. Well, that's no surprise. The spherical harmonics were eigenstates of rotation. That's why this is the right basis to consider. And so, in fact, what we see is that X of Q here is equal to 4 pi over 3. There should be a minus plus here. That's the whole point. Sorry, that's stupid sign. So what we see here is that the three components of this rank 1 vector could be expressible in terms of x, y, and z, or expressible in terms of the x0, x plus, and x minus. These components are known as the spherical tensor components of position. From this, we define the following. Let this object is a function of x, y, and z, or equivalently a function of r, theta, and phi. There are, for a given L, there are 2l+1 different polynomials in x, y, and z, or equivalently 2l+1 different functions of r, theta, and phi. These objects are called the solid harmonics. And they are the 2l+1 components of a rank L irreducible tensor. The symmetric, for example, if I have looked at the symmetric traceless matrix with its 5 objects, those 5 objects are the 5 different Y2Ms. Those are the objects which are rotate into themselves under a rotation. So let me just conclude with one last point here, how we define this thing. Maybe it's getting late. I don't want to get too deep into it, but let me give you a little foreshadowing of where we're going. We've done a lot of math today. We're going to bring this back into the physics realm next week. But the point here is that our different tensor objects that we saw that are going to be important in looking at the interaction between the atoms and the electromagnetic fields are intimately related to objects that have a certain amount of angular momentum. So the dipole operator, the electric dipole operator, is a rank 1 tensor. It's like an object that has 1 unit of angular momentum. And thus, when we look at absorption of light by atoms, we have to conserve angular momentum. Angular momentum goes from the ground state into the excited state through the absorption of the photon. And thus, that determines the selection rules between which excited states I can go to through the absorption of light through a dipole approximation. If I have absorption through a quadrupole, well, a quadrupole is a rank 2 object, and therefore carries 2 units of angular momentum. So, for example, I can go from an S state to a D state through a quadrupole interaction. And so where we're headed here is using this geometric connection to angular momentum in order to ultimately derive the selection rules for absorption and emission of electromagnetic radiation. And to do that, we need one last ingredient here, which is the Bigger-Eckhart theorem, which I had hoped to get to today, but we'll do on Monday next week. So I recommend reading about that a little bit.